all the frequencies. So the hand wavy way of thinking about this is, as I stretch out my impulses in space, I have to shove all these impulses in frequency and time infinitely close together to make a solid bar. Okay? And that's one way of thinking about how the Fourier transform of an impulse train is another impulse train, and as they get bigger in space, they get closer in frequency. So now we can start to talk about sampling and aliasing. So before we do that, we have to talk about the notion of sampling at all and the notion and the idea of reconstruction. So here we have the idea of some nice smooth scene illuminated by a light source, and then we have an imaging system that captures the intensity at a bunch of discrete places. And of course, what we'd like to do is we'd like to take the captures from these discrete places and be able to reconstruct this nice smooth signal. That is, to know what that signal is. Let's talk a little bit about sampling. Sampling arises when we come up with this notion of how do you store a continuous signal in a computer, right? So here we have a continuous signal, and this is in 1D, and we're going to do a lot of our stuff in 1D today because it's easier to draw. And so the obvious way of representing that, it's actually not the only way, because you can imagine different clever basis kinds of things, but sort of a normal way of thinking about that is by samples. That is, you just take the samples at each different location and you write down what the value is. And once you have that set of samples, later what you want to do is reconstruct what the original signal was, right? And why do you want to do this? Well, maybe you actually want to use the signal. You want to play it, if this is audio, you want to play it through a speaker. And I don't need samples, I need a continuous voltage. Or maybe I want to do some sort of analysis or mathematical processing in terms of thinking about what this signal is. So essentially what you have to do is you have to guess what's going on between each of the samples. That's all you can do. You have the samples at discrete places, but you need to connect the dots, if you will. You need to fill in what's going on. And a lot of what we're going to talk about today has to do with what's actually going on when you think about taking a set of samples and then trying to guess what's in between. So to illustrate most of these points, we're going to use a 1D signal. So you can think of this like audio, all right? So here's an interesting audio signal. You see this signal? So this is time, okay? Goes this way. And it starts off with a low frequency and gets higher and higher and higher and higher and higher and stops. All right. If you were to play that sound, you would hear what's called a chirp. Okay, that's actually what it's called. It's called a chirp. Comes from radar, etc., whatever. It's something that has power in lots of different frequencies. So when you send a chirp out, no matter what the frequency response of the thing you might be hitting is, you'll get something back. It's also a nice way of being able to localize it. There are lots of good reasons to use what's called a chirp. But here's a chirp that has higher and higher frequencies. But it's a good signal to think about looking at aliasing. Continuing with thinking about the digital audio, we can think about sort of music or any other way of dealing with audio, right? When we record a sound, we have a microphone, and a microphone generates out a continuous voltage. By the way, you guys know how a microphone works? More or less, a microphone works the following way. We have a permanent magnet, and we've got an electric coil, all right, with some wires in it, and out of that coil comes another wire. And usually the coil is on a little springy mechanism. The permanent magnets are fixed. You speak, and that causes a pressure wave. A pressure wave causes the coil to move back and forth. When you move a coil of wire through a magnetic field, that induces a voltage. So that voltage comes out on that wire, and it's a continuous signal. But in order to encode this into a computer, we put it through what's known as an A to D converter, analog to digital converter, and we get out a bunch of samples. And then, by the way, in the old days, we used to put those samples on something called a CD, compact disc. You guys probably don't even buy those anymore. If you do, you only buy them to rip them. But basically, it's a set of samples, it's in a file, whatever it is, okay? When you go to play this thing, okay, what you do is you put your CD into your ancient CD player, it pulls out the samples, and then it goes through what's called a D to A converter, digital to analog converter, and then we take that continuous voltage and we put that out through a speaker, which, by the way, is almost exactly the same as a microphone, right? It's a coil of wire, you pump electricity through it, it generates a varying magnetic field, there's a set of permanent magnets that causes the speaker to move with respect to those magnets, and voila, out comes a continuous pressure wave. So let's talk about this sampling operation and then the reconstruction. So here we'll take as an example just a sine wave. Okay? So I collect a bunch of samples. If I collect a bunch of samples, then what am I going to do to reconstruct it? Well, it might be enough to basically just connect the dots and get back the next sine wave. All right? And so as long as I had enough dots, that's easy enough to do. So I have enough dots, I connect the dots. But what if we missed things going on between the samples? What if we don't have enough dots? All right? Well, not surprisingly, something's getting lost, right? Some information is getting lost, right? So here we're showing you, right? So I've got a dot here, I've got a dot here, and there's all this change going on in between that is not realized, or I should say not captured. Perhaps the surprising result, though, is that actually this is indistinguishable from a lower frequency, okay? So here what's drawn in is this is the same set of dots that we had before, but there's a low frequency sinusoid that fits through there, okay? Continuing with that, with sort of the surprising result, is that the low frequency, that was always indistinguishable from those high frequencies if you only gave me a small number of dots. Okay, that is, I can't tell whether or not it's a high frequency or a low frequency. And that's the definition of aliasing. Or I should say that's the example of aliasing. The definition is it's a signal that travels sort of in disguise of another signal or of other frequencies. All right? Now we're going to make this formal in just a minute, but that's what's going on in aliasing, is that I've got a signal and I can't distinguish between a low frequency that was in there and actually a high frequency. By the way, this also happens in time. Have you ever watched a video where an airplane propeller is starting to go, and then all of a sudden you start to kind of see it spinning backwards, and then you see it spinning forwards? Okay, airplane propellers don't spin backwards. They only go forwards. So what's going on there? Oh, and by the way, I hope you know that if you were actually standing out on the tarmac watching the airplane, you wouldn't see this phenomena. The reason you're seeing this phenomena is that this was recorded on either video or film that was taking a picture every so often. And that's what's displayed here. Imagine we have this wheel that's turning this amount each time. So if you track the dot, you can see that the thing is turning almost 90 degrees at every rotation. But if that dot wasn't there, you would actually see this thing going backwards just a little bit, because of the fact that you couldn't tell which one of those cross patterns was which, and so you would see it rotating backwards, okay? And that's aliasing in the temporal domain. We'll talk about that in a minute. In the spatial domain, and essentially the thing is moving too fast for how often you're sampling at time for you to actually be able to tell what's going on. The high frequency and the low frequency can't be distinguished. To show you a simple example in an artificial image, we'll see some natural ones later. Here we have a rendering, and as this checkerboard gets further away from you in the distance, right, it's supposed to start getting thinner and thinner and closer, and you'll notice that somewhere right around here, it starts to break up. It's not looking like a checkerboard look. In fact, look at this nonsense, right? It's like low frequency all over again. What's going on? Well, we can look at that in MATLAB, all right? Suppose we have this input signal. Okay, this is like that chirp that I was showing you before. Well, we can plot this as an image in MATLAB, and that would look like this. Okay, so here I'm just doing x from 0 to 5 by 0.05, and I did this image of sine of 2 to the x times x. All right, and what you're seeing is, so it starts off a slow frequency, and then it's getting higher and higher, and eventually you start to see stuff that looks like that. So what's going on there? Well, that's aliasing. There are not enough pixels in the plot for you to be able to see what's going on. And that's illustrated down here where we have a small number of samples, a not dense enough sampling in order to recover those frequencies. So the question is, how can we prevent aliasing from happening? One is we could get more samples. Okay, we can join the megapixel craze in the current video technology. My birthday's coming up this month, and I treated myself to a new camera. And the camera has 36 megapixels in an image, all right, so that I can pull out really fine detail in a portrait. But in general, the sort of the megapixel thing doesn't go on forever. You know, stuff always can wiggle faster and faster as things get further away, for example. So what do you want to do? Well, what you want to do is you want to make sure your signals are less wiggly. That is, they don't have all that high frequency component. You want to get rid of some of that information. So the idea is we're going to get rid of some of the high frequency information, but that's going to be better than aliasing, right? The idea is we don't want to see that weird checkerboard effect, right? So we're going to remove some of the high frequency, but the idea is that the thing will be well behaved. So let's talk about that real quickly in our audio example. What we're going to do is we're going to introduce low pass filters. And what the low-pass filter is going to do is we're going to put that right here, so where the analog voltage is coming out of the microphone, so that the signal that goes into the A to D converter doesn't have frequencies higher than a certain amount. We'll say, okay, great. So that says that we can reduce the number of samples we need to take, or limit the number of samples we need to take. And then when we do the reconstruction, we'll know that anything that was reconstructed that was of a higher frequency than we let in should be thrown away. So we use the low-pass filter again for the output to the speaker. So that's the hand-wavy version about aliasing. Let's be big boys and girls. Let's do this in the frequency domain. A little bit of math. The first thing we need to do is define a comb function, which is the same thing as an impulse train. So a comb function is written this. I'm not sure we've defined what this Kronecker delta function is. Basically, it's a function that's a pulse of 1 when its argument is 0 and it's 0 otherwise. And what this would mean here is as k goes from minus infinity to infinity, this thing would count up by m's. So every m would be a 1. So if this is 2, then this would be a separation by 2's of this impulse train. Okay? So if m gets bigger, my pulses get further and further apart. Okay, that's an impulse train. As I said before, the Fourier transform of an impulse train is another impulse train. But also, as I said before, as the spacing gets larger in space, it gets narrower in frequency. Remember, that was the scaling property of the Fourier transform. So the less often we sample in space, the higher the samples in frequency. Okay? So that's in 1D. We can also do impulses in 2D, and that's called a bed of nails, because instead of just having a train of pulses that land on the integers or some multiple of integers in 1D, it's actually lying on all the discrete coordinates in 2D, which if you're in a macabre sort of mood, you can think of as a bed of nails. So that's written here, comb of mn, because we have a separation both in the x direction and in the y direction. And also, in the same way that the Fourier transform of an impulse train is an impulse train, the Fourier transform of a bed of nails is another bed of nails. And again, as the nails get further apart, the Fourier ones get closer together. And you can think of it from the same reason. If I spread the nails out infinitely far away and I get just a single pulse in the middle of the bed, I would not recommend lying down on that single nail. That would hurt. But if you think of it as an image, it's a single impulse. If you convolve that with your image, you'll get back the entire image. So you have to cover all the full plane in the Fourier space, okay? And so you have to shove all those Fourier nails back together to make a flat board that you could lie on. For the discussion about aliasing, though, I'm just going to talk about this in 1D because it's a lot easier to draw the pictures and to make it clear. So, hang on. What we're going to do is we're going to now talk about aliasing in the Fourier space, and we're going to talk about sampling a signal. And we'll first talk about sampling a low-frequency signal and then a high-frequency signal. Here we have a function. Here we have some nice function f, and it's a nice smooth function, let's say. All right? And it has some Fourier spectrum like this, f of u, and you'll notice that it's kind of limited, right? It doesn't have very high frequency components, like no high frequency components, very, very low. And here's our comb function pulse train, okay? And as we said before, the Fourier transform of that pulse train is another pulse train. And if the separation of the pulse train in space is m, then in frequency it's 1 over m. Now comes the point that's not so obvious. Suppose I want to take samples of a continuous function, right? I want to take a sample here and a sample here and a sample here and a sample here and a sample here. And I wanted to do it with a spacing of m. How would I do that? I actually have what I need here. I just multiply this times this, and I get this. All right?